Welcome to Astro Odyssey. Explore the universe. For most of human history, the universe was assumed to be static and eternal and changing, unmoving, simply there. The stars were fixed points, the galaxies unchanging islands of light. Even when Einstein first developed general relativity, his equations predicted a universe that should either be expanding or collapsing. And that idea was so unsettling that he added a mathematical fix to hold the universe still. But the universe refused to cooperate. In the 1920s, astronomer Edwin Hubble made a discovery that shattered humanity's assumptions. Forever distant galaxies were moving away from us. And the farther away they were, the faster they were receding. Space itself was stretching. The universe was expanding. This wasn't an explosion into empty space. It was space itself growing, carrying galaxies along like raisins embedded in rising dough. That discovery didn't just change astronomy. It changed reality. Once expansion was accepted, scientists asked the next logical question: how fast is the universe expanding? The answer seems straightforward. Measure the distances to galaxies, measure how fast they're moving away, and calculate the rate. This expansion rate became known as the Hubble Constant. For decades, astronomers refined their measurements, proving telescopes, correcting errors, and narrowing uncertainty. Slowly, confidence grew. By the late 20th century, it seemed like cosmology was becoming a precision science. The universe had a known age, a known expansion history, a known composition. Matter, dark energy, everything fit together into a beautiful, elegant model. Or so it seemed. Then something strange happened. As measurements became more precise, the answers started to disagree. When scientists measured the expansion rate using nearby galaxies, objects close enough that their distances could be measured directly, they got one value. But when they measured the expansion rate using the early universe, it's by looking at the faint afterglow of the Big Bang itself, they got a different value. Not slightly different, significantly different. And no matter how carefully they checked their work, the discrepancy refused to go away. This problem became known as the Hubble Tension, and it is now one of the biggest unsolved mysteries in modern physics. To understand why this is so disturbing, we need to understand how these measurements work. The first method uses what astronomers call the cosmic distance ladder. It starts with nearby stars whose distances can be measured directly through parallax, the tiny shift in position as Earth orbits the Sun. These stars help calibrate brighter objects, like Cepheid variable stars, which pulse at predictable rates. Cepheids act like cosmic yardsticks. Once calibrated, they allow astronomers to measure distances to nearby galaxies. From there, even brighter objects like Type Ia supernova extend the ladder deeper into the universe. This method is built step by step, each rung resting on the last. And when astronomers use it, they consistently measure a faster expansion rate, about 73 kilometers per second per megaparse. The second method looks far deeper in time. Instead of measuring today's universe, it examines the universe as it was just 380,000 years after the Big Bang. At that moment, the universe cooled enough for light to travel freely, releasing what we now see as the cosmic microwave background, a faint glow filling all of space. This ancient light carries an extraordinary amount of information. Tiny temperature fluctuations encode the density, composition, and geometry of the early universe. By fitting this data into our cosmological models, scientists can infer how fast the universe should be expanding today. And when they do, they get a slower value, about 67 kilometers per second per megaparsec. Both methods are incredibly precise. Both are independently verified. Both are trusted. And yet, they cannot both be right. At first, Scientists assumed there must be a mistake. Maybe distances to Cephids were slightly off. Maybe dust was interfering with measurements. Maybe the early universe models were incomplete. Years were spent refining techniques, recalibrating instruments, and cross-checking data. The uncertainty bars shrank, but the gap between the two measurements remained. In fact, as measurements improved, the tension became stronger. The disagreement passed the threshold, where physicists stop saying that's odd and start saying something is wrong. If this were a minor discrepancy, it wouldn't matter much. But it isn't. The expansion rate affects everything: the age of the universe, the formation of galaxies, the behavior of dark energy, and the fundamental laws governing space and time. If the Hubble tension is real and all evidence suggests it is then our standard model of cosmology is incomplete. That's where the discomfort begins, because the current model, known as lambda CDM, has been extraordinarily successful. It explains the cosmic microwave background. It explains galaxy formation. It explains large-scale structure. It fits decades of data with remarkable accuracy. And yet this single number refuses to align. It's as if the universe is quietly telling us that something important is missing. We don't yet know what it is. Some scientists suspect the problem lies in the early universe. Perhaps there was an unknown form of energy present shortly after the Big Bang, something that briefly altered the expansion rate before fading away. This hypothetical early dark energy could reconcile the measurements without breaking known physics. Others think the issue lies with gravity itself. Maybe general relativity, which works perfectly on small scales, behaves differently across billions of light years. Or maybe dark matter interacts in ways we haven't yet detected. There are even more radical possibilities. Some physicists wonder whether the universe contains additional dimensions, hidden fields, or unknown particles influencing cosmic expansion. Others question whether our assumptions about the homogeneity of the universe, the idea that it's roughly the same everywhere, might be flawed. Each possibility carries enormous implications, not just for cosmology, but for physics as a whole. What makes this moment so remarkable is that we may be standing at the edge of a scientific revolution. Many of the greatest breakthroughs in physics began with small inconsistencies, tiny cracks, in otherwise successful theories. Mercury's strange orbit led to general relativity. Blackbody radiation led to quantum mechanics. Now, a disagreement over the expansion of the universe may be pointing us toward the next transformation in our understanding of reality, and the universe isn't waiting for us to catch up. New telescopes are already gathering data. The James Webb Space Telescope is measuring distant galaxies with unprecedented precision. Upcoming surveys will map millions of galaxies across cosmic time. Each new observation will either resolve the tension or deepen it. If the universe really is expanding faster than we thought, then our story of cosmic history from the Big Bang to the present moment will need to be rewritten. And that raises a profound question. If we were wrong about something this fundamental, what else might we have misunderstood? This is only the beginning. To understand why the Hubble tension might signal new physics, we need to look at what actually drives the universe's expansion today. In the late 1990s, astronomers made another shocking discovery. Not only is the universe expanding, but that expansion is accelerating. Distant supernovae appeared dimmer than expected, meaning they were farther away than they should be. Something was pushing galaxies apart faster and faster over time. That something was named dark energy. And despite making up nearly 70% of the universe, we still have no idea what it truly is. In our current model, dark energy is treated as a constant property of space itself, unchanging, uniform, and eternal. But the Hubble tension is forcing scientists to ask a dangerous question. What if dark energy isn't constant at all? If dark energy behaved differently in the early universe than it does today, it could explain why expansion measurements don't agree. A brief burst of extra energy shortly after the Big Bang could have sped up early expansion, changing how sound waves traveled through the primordial plasma. That would alter the cosmic microwave background in subtle ways, leading us to miscalculate today's expansion rate when we look backward in time. This idea, known as early dark energy, is attractive because it fixes the math without destroying everything else. But there's a problem. No direct evidence for it exists yet, and adding new components to the universe always risks turning elegant physics into mathematical patchwork. Another possibility is even more unsettling. What if gravity itself is the issue? General relativity has passed every experimental test we've thrown at it. But those tests mostly happen within our solar system, or our galaxy. On the scale of the entire universe, gravity may behave differently. If space-time curves or evolves in ways Einstein never predicted, then our calculations of cosmic expansion could be fundamentally flawed. Modified gravity theories attempt to explain this, but they often create new problems elsewhere, breaking things we already understand. Fixing one crack can cause 10 more. Then there's dark matter, the invisible substance holding galaxies together. We know it exists because of how galaxies rotate and how light bends around massive objects. But we don't know what it's made of. If dark matter interacts with radiation or dark energy in unexpected ways, it could subtly alter the universe's expansion history. Some models suggest dark matter may decay, clump differently, or even exchange energy with dark energy over time. Each of these ideas is speculative, but together they point to a deeper truth. We may not understand the dominant components of the universe nearly as well as we think we do. What makes the Hubble tension so compelling is that it doesn't disappear when you ignore it. Independent teams using different telescopes, different methods, and different assumptions all keep finding the same disagreement. Gravitational lensing, baryon acoustic oscillations, and time delays in distant quasars are now being used as additional checks. And while some results fall between the two main values, none cleanly resolve the conflict. The universe seems stubbornly inconsistent. This has led some scientists to question a foundational assumption of cosmology: that the universe is smooth and uniform on large scales. We assume that, on average, matter is evenly distributed. But what if our local region of the universe is unusual? What if we live inside a vast, underdense region, a cosmic void that makes expansion appear faster nearby than it truly is overall? This idea sounds extreme, but it's testable. So far, observations suggest it's unlikely, but not completely impossible. And when physics reaches this level of uncertainty, even unlikely ideas stay on the table. What's remarkable is how small the difference actually is. Just a few kilometers per second per megaparsec. On human scales, that's nothing. But across billions of light years, it compounds into a radically different universe. Small errors, stretched across cosmic time, become existential problems for theory. This is why physicists are taking the Hubble tension so seriously. It's not about one number. It's about whether our entire framework for understanding the universe is fundamentally incomplete. History suggests that when nature refuses to fit our models, the models eventually break. And when they do, something deeper emerges. The Hubble tension may be the first clear sign that the next era of physics is approaching, one that unites gravity, quantum mechanics, dark matter, and dark energy into a single coherent picture. Or it may reveal that the universe is more dynamic, more complex, and more surprising than we ever imagined. As new data continues to arrive, the tension may finally resolve, or it may grow impossible to ignore. Either outcome would be revolutionary. If the numbers align, will confirm our current theories with unprecedented confidence. But if they don't, we'll be forced to admit something extraordinary, that the universe has been telling us a deeper story all along, and we're only just beginning to hear it. And that brings us to the most unsettling possibility of all. What if the universe isn't just expanding faster than we thought? What if it's doing so for reasons we don't yet have the language to describe? To understand where this mystery may be leading, we need to look not just at how fast the universe is expanding, but where that expansion is taking us. Expansion is not a background detail of the cosmos. It determines the ultimate fate of everything that exists. Galaxies, stars, planets, even atoms are all bound together by forces that must constantly fight against the stretching of space. For most of cosmic history, gravity slowed expansion down. Matter pulled matter together. Structures formed. Galaxies collided and merged. The universe became richer and more complex over time. But dark energy changed that trajectory. Roughly 5 billion years ago, expansion stopped slowing down and began speeding up. Since then, the universe has been pulling itself apart faster and faster. If the expansion rate really is higher than we thought, then this acceleration is even more aggressive than our models predict. That has profound consequences for the future. Over immense timescales, distant galaxies will slip beyond our cosmic horizon. Their light will never reach us again. The observable universe will shrink, not because the universe is getting smaller, but because more of it is becoming unreachable. Future astronomers, if any exist, may look out into the sky and see only their own galaxy, surrounded by darkness, unaware that billions of others ever existed. But the implications may go even deeper. If dark energy changes over time, if it grows stronger, weaker, or behaves unpredictably, then the universe's fate could be dramatically different from anything we've imagined. In some scenarios, expansion continues forever, slowly thinning the universe into a cold, dark emptiness known as the heat death. In others, dark energy strengthens, eventually overwhelming every force in nature. Galaxies would be torn apart. Stars would unravel. Planets would disintegrate. Even atoms could be pulled apart in a catastrophic finale called the Big Rip. While this outcome is still considered unlikely, the Hubble tension forces scientists to admit that we don't yet know enough to rule it out completely. There is also a quieter, more unsettling possibility. The universe may not end in a dramatic explosion or tearing apart, but in a gradual loss of structure and meaning. Expansion could isolate regions of space so completely that communication, travel, and even shared physical laws become impossible across cosmic distances. The universe would fragment into countless disconnected islands of reality. Each region would evolve independently, governed by the same equations, but forever separated by the expansion of space itself. What's striking is how closely this cosmic uncertainty mirrors our theoretical uncertainty. The faster expansion rate doesn't just affect distant galaxies, it undermines the assumptions we use to describe reality at the largest scales. Cosmology relies on the idea that the universe follows simple, universal rules. But the Hubble tension suggests that those rules may change depending on when and where you look. Time itself may play a more active role in shaping the laws of physics than we ever expected. Some physicists are beginning to wonder whether space and time are not fundamental at all, but emergent byproducts of deeper informational or quantum structures. If that's true, then expansion might not be a property of space, but a consequence of how information unfolds across the universe. In that picture, the Hubble tension wouldn't be an error to fix, but a clue, a signal that our description of reality is incomplete at the most basic level. This is why the tension matters so much. It's not just about measuring the universe more accurately. It's about discovering whether the universe itself is more complex than our best theories allow. Every time scientists push the boundaries of precision, nature responds with another layer of mystery. The closer we look, the less certain the foundations become. And yet this uncertainty is not a failure of science. It is its strength. Physics advances not when everything fits perfectly, but when something refuses to fit at all. The universe is not obligated to make sense to us. It reveals its secrets slowly, often reluctantly, sometimes only when our assumptions collapse under the weight of new evidence. Right now, we're living through one of those moments. The universe is expanding faster than we thought, not because our instruments are broken, but because reality itself may be more subtle than our models can capture. Whether the answer lies in dark energy, gravity, hidden particles, or something entirely unexpected, one thing is certain: the solution will change how we understand the cosmos, and perhaps that's the most humbling lesson of all. The universe has been expanding for nearly 14 billion years. It has watched stars be born and die, galaxies collide, and civilizations rise and vanish. And only now, at this tiny moment in cosmic history, are we beginning to realize that we may not yet understand the rules that govern its growth? If the universe is expanding faster than we thought, then it's not just moving away from us, it's moving beyond our current understanding. And the question we face next is not whether we can measure it more precisely, but whether we are ready to rethink reality itself. As scientists confront the possibility that something fundamental is missing from our understanding of the universe, attention is now turning to the future, because the next decade of observations may decide whether the Hubble tension is a temporary puzzle or the beginning of a paradigm shift. New instruments are being designed not just to refine old measurements, but to attack the problem from entirely new angles. Instead of relying on traditional cosmic distance ladders or early universe models, researchers are developing independent methods that bypass many of the assumptions that could be hiding the truth. One of the most promising tools is gravitational waves. When massive objects like neutron stars collide, they send ripples through space-time itself. These events act as standard sirens, cosmic signals whose distance can be measured directly from the strength of the waves, without relying on complex calibration steps. If enough of these collisions are observed across the universe, they could provide an entirely new way to measure cosmic expansion. Early results are still limited, but as detectors become more sensitive, gravitational waves may become one of the cleanest tests of the Hubble tension yet. Meanwhile, the James Webb Space Telescope is already reshaping our view of the universe. By observing distant galaxies with unprecedented clarity, it allows astronomers to measure stellar populations, galactic structures, and distances in ways that were impossible before. Webb's data may confirm the faster expansion rate or reveal hidden systematic errors in earlier measurements. Either outcome would be transformative, and Webb is only the beginning. Upcoming missions, like the Euclid Telescope and the Vera Rubin Observatory, will map the universe on colossal scales, tracking billions of galaxies across cosmic time. But even if new observations confirm the tension beyond doubt, the real challenge will be interpreting what it means. Physics does not change easily. Every new idea must survive relentless testing, mathematical consistency, and experimental verification. If dark energy is evolving, we must explain why. If gravity behaves differently on cosmic scales, we must reconcile that with everything we already know. If new particles or dimensions exist, they must leave traces we can detect. The universe may be hiding its secrets, but it never hides them completely. What's remarkable is that cosmology has reached a point where precision itself is driving discovery. For centuries, the biggest questions in astronomy were answered by simply seeing farther and clearer. Now, we are limited not by vision, but by understanding. The universe is measured so precisely that even tiny mismatches can expose deep flaws in our theories. This is a sign of maturity in science and also a warning. When models become too comfortable, nature finds ways to disrupt them. There is also a philosophical weight to the Hubble tension that cannot be ignored. Humans have always tried to reduce the universe to simple rules, elegant equations, clean symmetries, predictable outcomes. But the universe may not owe us elegance. It may be governed by layers of laws, each emerging from deeper ones, each valid only within certain limits. Expansion may not be a single phenomenon with a single explanation, but a process shaped by multiple forces across time. If that is true, then the Hubble tension is not a mistake, it is a message. A signal that our current description of reality is an approximation, not a final answer. And that realization places us in a familiar position. Every time humanity has believed it understood the cosmos, a new discovery has expanded the boundaries again. Earth was not the center. The sun was not unique. The Milky Way was not the entire universe. And now perhaps, the laws we rely on are not the whole story either. What happens next depends on how willing we are to listen to what the universe is telling us. The coming years will either reinforce the foundations of modern cosmology or force us to rebuild them. Both outcomes are extraordinary. Either we confirm our deepest theories with stunning accuracy, or we open the door to new physics that reshapes our understanding of space, time, and existence itself. And standing at this crossroads, one truth becomes clear. The universe is not just expanding faster than we thought. It is revealing that knowledge itself is still expanding, pushing us beyond certainty, beyond comfort, and toward a deeper, more mysterious reality at the deepest level. The mystery of the universe's expansion is not just a technical problem for physicists, it is a reminder of our place in a cosmos that is far larger, older, and more complex than human intuition was ever designed to handle. The fact that we can even ask these questions is extraordinary. On a small planet orbiting an ordinary star, intelligent beings evolved who learned to read the faint afterglow of the Big Bang. Measure the motion of galaxies billions of light years away, and notice when reality itself refuses to behave as expected. That alone is remarkable. Yet the Hubble tension shows us that knowledge is not a straight path towards certainty. It is a process of constant revision. Each generation inherits a model of the universe that feels complete until new evidence quietly undermines it. The expansion of the universe once shocked astronomers. The discovery of dark energy shocked them again. Now, the possibility that we may be missing something fundamental threatens to rewrite the story once more. This is not a failure of science. It is science working exactly as it should. What makes this moment unique is that the discrepancy is not coming from ignorance, but from precision. We are not confused because our data is poor. We are confused because it is too good. The universe is being measured so accurately that its smallest inconsistencies are becoming impossible to ignore. And those inconsistencies are where progress is born. Somewhere within the Hubble tension lies a deeper truth about the nature of reality, whether it involves hidden forms of energy, unknown particles, evolving laws of physics, or concepts we have not yet imagined. There is a certain humility in recognizing that even our best theories may only describe a chapter of a much longer story. The universe does not rush to explain itself. It unfolds slowly, revealing its structure one mystery at a time. And each time we think we have reached the end of understanding, it offers a new question instead. Expansion is not just something the universe does, it may be something knowledge itself mirrors. Always moving outward. Always incomplete. In the far future, civilizations may look back at this moment as a turning point, the time when humanity realized that its cosmological model was not final, but provisional. or they may see it as a resolved puzzle, a brief anomaly corrected by better data and deeper insight. Either way, the pursuit matters, because the act of questioning, of refusing to accept easy answers, is what drives understanding forward. The universe has been expanding since the beginning of time. Galaxies have been drifting apart long before Earth existed, long before life emerged, long before humans looked up and wondered what was out there, and long after we are gone, expansion will continue, shaping a future we can barely imagine. But right now, in this brief window of cosmic history, we have the ability to notice when something doesn't add up, and the curiosity to investigate why. The universe may be expanding faster than we thought, but so is our understanding, and that may be the most important discovery of all.